Kalau pencet terus sebelahnya nggak bisa. Tapi itu nggak asli itu kita itu punya itu limited ya. Lo pasti disuruh
kemarin bom kecil habis dari area juga.
Ini berapa sih? Ini masih sama. Ini berapa?
Gue ingat soalnya saya ambil kode dulu itu dia
Oh ya ya ya. Enggak yang ini ada tahu ikut acara apa gitu. Testo gue rambut.
Harus mau kan sih. Ya, harus mau kan. Lu kayak gini. Ini apa? Woi, dia mau berpengalaman ya. Modelnya apa? Modelnya apa? Mas, mohon. Mas ini habis ini. Bapak, Hansan lagi di roasting semuanya nih. I like your cut, G. I like your G jadi apa?
Udah mau ada parahnya itu Pak.
Besok coba komen. Gini. Atasan ya, kayak jidat tuh.
Gosh, damn! Bro, calm down, bro. Calm down, man. Too much. Ready, fire. Terus sekarang lampu. What? Okay, everybody got that?
Stop. Oh, misalnya kalau cuman berpikir smart itu kan karena kalau terpunya maksudnya
bayar itu tapi lama sih aku bayar lagi
Oh, look, it's the thing that raises something. Am I wrong though? Mereka salah kan? Okay, so we arrive at the next topic, which is quality inspection systems. Let's review a little bit. What are the typical candidate processes for automation? When you look at a factory doing something manually, what processes do you usually pick?
Quality control.
There's certainly one of it. But what are the conditions? What are the types? How do you select? What are the factors that you consider to be a good candidate for automation? No, not about quality. But when you see a factory from beginning to the end, you know, you make what, a ballpoint pen, for example, a pen, right? You have some injection molding, you have some assembly, you have some, you know, until you get a pen at the end in a package of a box. So from the very beginning to the end, how do you select the process to automate? The ones that are ... What kind of characteristics? Huh? Repeatable in what sense? Okay. The dimension is fixed, etc. Right? Yeah. Repeatable. Remember the term zero value added. Okay, what does that mean? Zero value added. Okay. What do you mean by value? What are examples of value added processes? Modifying the parts. Adding features.
Reducing costs.
No, to the product, like adding value to the product. So when you machine something, that's value adding, right? When you assemble things, right? That's value adding. Previously it was 2 parts, now it's 1 part, and it's functioning now, right? I mean, you fill the ink to the pen. So previously the ink is unusable. You pour it in, it's usable. That's value. So zero value added processes then would be, for example, material handling. You move it from A to B. Logistics. It's not adding value, at least in the factory, right? I mean, logistics from the factory to the consumer, yes, that's value adding. But from the warehouse to the assembly point, no, that's not value adding. Okay, so zero value adding processes are the ones that, you know, you try to automate the most. Quality inspection system is one of them, right? Because it's something you have to do, but you don't want to do it if you don't have to, right? If your process results in 100% yield, you wouldn't have this. So this is like a necessary evil kind of process. This is what you automate because you want to spend as little as you can to get this done, right? So we'll talk about quality philosophy, types of quality inspection, and the technologies we can use for that. Okay? I remember one of the first internship I did is a brake pads manufacturer, brake systems, okay, automotive brake systems. And they have this big banner in front of the factory. Right the first time, right every time. Okay, why do you think it's important? Right the first time, right every time. Think of setting up a machine. I mean, this factory is relatively automated. But even with automation, there is some tuning that you have to do, right? You have to set up the machine. And setting up the machine, if you don't set it up right or optimal, then you'll have some defects. So right the first time, meaning like when you first turn on the machine, sometimes things become a bit off, okay? The temperature isn't right, the machine is not all warmed up, so sometimes you'll have defect at the beginning of the shift. So let's say I'm the first shift from, I think our first shift was from 7 a.m. to 4 p.m. and then second shift is, no, to 3 p.m. and then second shift is 3:30 to 12 midnight. And when they're behind in schedule, then they'll have a third shift, which is basically running the plant 24 hours. So at the beginning, when I step into my shift, I turn on the machine or I set up my thing, right? Okay, today I'm producing part A 600 units, right? So I set up the machine to injection mold something, for example. But there are usually some parameters that is always up to the operator, like the cooling time for the mold. Maybe 15 seconds was okay yesterday. Today, it's a bit hot day and the weather is different, or I don't know, some
External factors.
yeah, you just never know, right? So the machine just behaves sometimes differently. So when I set the machine up, usually there are some first parts that become rejects, and that becomes cost. Not for the part itself, but for the time usually, because the whole assembly machine cannot run until that's done, right? So everybody's setting up their machine, and usually the first 15 minutes, 20 minutes is kind of setup time. But if you do it right the first time, then that setup time becomes minimum, and we can get more things out the door in 8 hours shift. So right the first time, right every time. I think that's a cool slogan, right? As operators of the machine, that's what you have to do. And so that's what I just said, first part sampling. Because if you just turn on the machine and then you let the injection molding run, boom, 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 and then you have 100 parts with defect, that's cost. So you produce one first, pause the machine, and then do the sampling of the part, check the dimensions, is everything good, right? Sometimes there are jigs, you put it into the hole, okay, this is a go gauge, a no-go gauge, right? So it has to go on this hole, but it may not go on this hole. So those are called jigs or gauges you can use. Okay, now as the machine goes for that entire 8 hours, again, external factors, things might change. Some temperatures start to drift, some tools become dull. So let's say you have a machine that stamps paper, the food containers, for example, right? Food containers, you got the template, right? They punch it from the paper, and then let's say the tool becomes dull. Maybe some cut is not cut completely. That's defect. So random part sampling is also important. So first part, and then as the 8-hour shift goes, sometimes every hour I just pick one part, measure it, still good. Okay, let's keep going, right? So that's what I just said about machine setup and tuning. So there are some different ways you are going to do quality check. And the most obvious one is kind of a contact method, right? You do some measurement, you do some measurements and you evaluate whether it's still within spec. Now, in terms of dimensional checking, for example, I don't know whether there should be any sound or not. Okay, maybe there is no sound. Okay, no sound. So this machine is doing a measurement of the dimensions. So the probe actually measures different points on the part, and this can be automated. So they come up with a report, something like that. Okay. A more fancier device.
The Rama tube inspection system can inspect and measure.
Regenerative braking is a really clever way of using the kinetic energy of the car, its forward motion, to recharge your battery. You can do this with the parts that are already in your EV. You don't need to add any additional equipment. The parts that are in there can already do this. They just need to be programmed to do so.
Okay. So this is called a roamer arm. I think it's actually a brand, roamer, R-O-M-E-R. But what it can do is it can actually scan any object with this laser scanner, and you go through this tube, for example, and make sure it is within spec.
Around metallic and non-metallic wires, tubes, and pipes. It enables tube manufacturers in sectors such as automotive, aerospace, shipbuilding, medical, machinery, appliance or power generation to become more productive. It is based on the Romer Absolute Arm, a universal portable metrology tool with a measurement volume of up to 4.5 meters. Users can choose from 6 different non-contact probe sizes.
This is non-contact.
Line-E mode. The Romer Tube Inspection System is a portable 3-in-1 solution. It represents a
So at the end there is a laser scanning probe.
unified system covering the 3 main applications of tube inspection and definition, geometry measurement, and vendor interfaces with online bending program correction based on one tube sample. This ensures a short setup process of bending machines and helps to reduce scrap. No matter where you need to measure, the system is set up in just a few simple steps. It is the only portable tube inspection solution on the market. The Romer Tube Inspection System can be taken to the workpiece to measure pipes, lines, hoses, and tubes in place, thereby saving time and effort. Reverse engineering tube geometry for replacement parts is fast and straightforward, even in place on the assembly without removing the tube from the machine. The solution includes a Romer Absolute Arm, an inspection table, a system computer, software, and various.
So based on the laser scan, they can actually construct the 3D digital twin of it.
Accessories. System can.
So can anybody tell me how this thing works? Just make a guess. So the laser scan can detect like the contour, right? Can detect the contour of the tube, including measuring the diameter. But why do you need the arm? What's that arm for?
Distance?
Distance. What do you mean by distance? I'm trying to measure the tube, right? Distance from what?
The length of the tube?
Okay. Tell me more. How are you going to get the length of the tube?
I guess you can get the coordinates from the X, Y of the arm
Mm-hmm.
and map it out.
Okay, so what do you think is in the arm? Anybody want to make a guess?
Rotary encoder?
Yeah? The angles, right? Now, if I tell you the angles of... So this is not a robot arm. There is no actuators here. They're all sensors. So if I know where I mount the arm, the base of it, and then I know that angle and that angle, each angle of the arm, can you calculate the X, Y, Z coordinate of this end? Yeah? Not in your head, obviously, but yes, it is possible if you know those angles. It's called coordinate transformation. So once you know X, Y, Z coordinate of this thing, and then the next time you scan, it always tracks. Every time you scan that point, where is that point in space? And so it can create the 3-dimensional chart of it. Right? Does that make sense? Yeah? So this is called the rover arm. It is still cheaper than a CMM. Before this technology, we use what is called a CMM. It's a coordinate measuring machine. It's huge, it's expensive. You know, it can be like 4 of this table combined, and it's very temperature sensitive. Basically, there is a probe that comes in and touch touches it, like the previous video we see. But that's a much smaller CMM. A big CMM would have a table that is perfectly calibrated. You know, when I attended college in Ohio State, 1996, they had one of these in a spatial room. They regulate the temperature, and it's very expensive machine. Yeah.
I think we forgot a little bit 3 minutes ago.
But I'm not in the mood, so. Okay. This thing can replace this three-dimensional table that actually measures things with touch. This one is non-contact and very compact. It's not temperature sensitive. It's relatively portable, and it's cheaper. So cool. Let's take a look at this guy. Oh, same thing.
Packages. Next, we have the Romer 7-axis hard probing and laser scanning arm.
So this one is compact, but it's still a roamer arm.
If the arm is on, it's ready to operate. First, we have the Romer 6-axis hard probing arm. This arm has the ability to run battery and Wi-Fi, eliminating cables on the shop floor. An operator can use the arm on the shop floor to perform inspections, machine setups, and fixture builds. A person can quickly measure their parts and get immediate feedback of in and out of tolerance conditions. The Romer can also be utilized by your inspection team to perform full first article inspections using many different software packages. Next, we have the Romer 7-axis hard probing and laser scanning arm. These arms offer the same shop floor ready hard probes as the 6-axis arms, but also add a 3D non-contact laser scanner.
Yeah, we saw the laser scanner. This one is the contact version. Okay? Now, obviously, the most common inspection is not only dimensions, but also presence of a part. Like, for example, if it's missing this button, you gotta see some visual check. And machine vision is one of the most common quality inspection systems because it simulates human, right? Obviously. So we replace the human inspection, which is actually not that reliable. Working 8 hours just seeing the same thing, making sure everything's there is just impossible and not human to do, right?
VeriSense vision sensors are a complete image processing system in the shape of a sensor. Their compact housing integrates everything required for an inspection task. Camera with lens, illumination, hardware and software for image processing, and of course, interfaces. After a one-time configuration in 4 intuitive steps on a PC, VeriSense is ready for results. Up to 20 different image tools are available for simultaneous object inspection. Where required, the results can be compared against the targets in any industry and across a wide application range. Molded parts can be instantly and completely inspected. Is there any overmolding? Are all fan blades generated? Is the insert part properly placed? Thanks to patented, contour-based VEX technology with 360 degrees VEX lock part location, VeriSense will detect the different fan blade positions. Mechanical part guidance is therefore completely unnecessary. Easy color inspection, like in vehicle electronics, often turns out to be a challenge. Is every color in the right place? Are all blanks in the defined positions? Is the fuse puller present? What the human eye perceives as brightness, hue and saturation is mapped by the VeriSense Color VEX Assistant in an interactive 3D color model for easy and intuitive color inspection. Flawless packaging and labeling is essential in food and beverage. This requires hygienic machinery design with IP69K rating. Is the best before date correct? Can it be read by humans? Is the label position accurate? Besides bar and matrix codes, VeriSense is able to read and evaluate plain text. The integrated web interface allows for convenient change of target values or other parameters and runs in the existing web browser of the machine control. Part inspection and sorting is an everyday occurrence in most industries. Which part is being inspected right now? Are all drill holes present? What is the part position? The typical rather large working distance in pick-and-place applications calls for powerful illumination. VeriSense directly flashes illumination with up to 4 amperes, which makes any external flash controller superfluous. Needless to say, VeriSense checks everything simultaneously with a single shot. Is everything in the package? Are chopsticks and wasabi included? Is the label position accurate? Is the best before date correct and easy to read? Is the proper barcode present? Is the right private label printed? A single VeriSense vision sensor performs up to 32 parallel feature checks in nearly any industry, flexible, easy, and intuitive. Find out more at www.
Okay, so that's kind of the overview of it. Let's look at a typical setup of a vision system. Obviously, you have the camera. What do you think that laser sensor is for?
To count the amount of product that is passed.
Okay, sure you can do counting, but what's its function in relation to the camera?
It is fully pass through. It fully passes through the laser or the area.
Why do you need to know that?
Most probably target.
This laser is just a trigger, by the way, right? I mean, it's not a laser scanner. It's just a laser trip that something is there. If you're the camera, what do you need to know? Position, right? Like, when am I supposed to take the picture? So, if this passes and trips the laser, and you know the speed of the conveyor, then you know when you should take a picture, right? So that laser is there to time when you're supposed to inspect.
Good. Is that properly placed?
And
Thanks to
this is also typical. You'll have a monitor for the human to actually see what they see, even though it's not like somebody watching it all the time, but it's typical to have a monitor to show these are the features you check. For example, it's green means good, right? Sometimes you're missing. So you can be missing features, you can
can
be
be
missing
instantly and
holes.
completely inspected. Is there any overmolding? Are all fan blades generated? Is the insert part properly placed?
Right, so for example, you're missing one or it's out of dimensions. You can measure up to pretty accurate sub-millimeter measurements can be done with good illumination. So the key here is a good illumination because that's why you see the flash. And if it's reflective, it's a bit tough. It can be challenging for reflective parts, but for vision in particular.
Thanks to patented variable electronics,
And there is
often
the,
turns out to be a challenge. Is every color present by the VeriSense color affects us?
There is the rejection mechanism, usually. So you immediately separate ones that do not pass, and then a human would then evaluate what's going on this part, right? So this is an inspection for PCB.
Well, this is our 3D automatic optical inspection machine. And what we have here is the loader here, the automatic loader, the boards are loaded in there. The scanning head is here. and the boards pass through and then into the automatic unloader at the rear. Most AOI machines function by taking a digital image in the 2 dimensions and do a comparison between a good board and the board under a test, and also do some image recognition to recognize characters on the surface, letters, numbers, to check that the right component is fitted, and also to check the orientation is correct, the right rotation. This machine does all that, but in addition, it takes a measurement of the 3-dimensional state of the board, and it does this on a 20 micron mesh. If you can imagine that over the surface of the board, on a pitch of 20 microns, it measures the height of every feature on the circuit board.
So it also takes a 3-dimensional contour of it. By doing that, you can actually detect the solder quality.
So this creates an enormous database of dimensions in the sort of z-axis. And from this database, the operator can program specific tests which measure the volume of solder joints on a particular component, or the height of a leg, a gold wing leg perhaps, to identify whether it's been lifted or not, or it might be the height of a board grid array to check that it's soldered perfectly flat. It can measure the inclination of the BGA to a very, very high accuracy. Now, obviously, you might be aware that if a BGA doesn't solder flat, potentially some of the balls underneath may not have been reflowed.
So what we are doing here is we're looking at component leads. In this particular, it's the 6W0827. And we're going to a tip of every lead using a locator, which can be seen here.
Okay, so you can look at the quality of a solder joint if a leg is lifted or not on that component.
We found all the leads, and now we've found all the leads. We go to the tip of the leads, and we measure a height check. So we do a mean height check for this one. We look at a little square here, and then this square shows us this data. This is all the points, all the ends of the leads put onto one graph. And this is what we allow through, and anything outside of this is failed. That's how we do all our lead checks. Shows any lifts, any faults, any fails, we'll find it.
Just to demonstrate the 3D capabilities of the machine, we can just look at the screen here, switch it to 3D mode, and say we want to look at this component here, just draw a box around it, and then you've got a 3D image of that component.
Look at that.
Rotate it there.
Beautiful, right?
Turn it around. Look at it from the other side.
It's a pretty
Now,
nice.
this isn't how we inspect the circuit boards, but it actually demonstrates the power of the data we've collected to recreate a 3D image. The beauty of this machine is that it enhances the inspection capabilities by a factor of 10. On a conventional 2D inspection machine, you might expect to find 99% of the faults, but with this added 3D dimension, you would expect, and we do, find 99.9% of the faults. So it improves the ability to detect faults by a factor of 10 over the traditional machines. And that means better quality assemblies.
All right. So that's visual inspection of a PCB. Let's look at a another different method of quality inspection.
Inspection on height verification system. It's custom designed by Compass Automation for an end user that required 100% inspection of several critical part features at a production rate of 5 seconds per part. The customer, Ramsell Engineering, is a leading provider of custom tooling, metal stapler, the 2-axis robot of part presence in the nest. The robot grips and places the part into the first fixture of a 7-station rotary table. The part indexes to the first inspection station under a 16-megapixel camera and custom lighting. The part is centered by a pneumatic gripper mechanism before the camera captures an image of the part.
So that pneumatic grip is only to center it, that's it. And then the camera takes the picture.
To measure 20 critical geometric features. Next, the table indexes the part to the Keyence LVDT sensors.
So this one is an LVDT displacement sensor. It's basically like a potentiometer. You can think of it. Do you remember what potentiometer is? The knob, but what does it measure? You adjust resistance using a potentiometer resistor, but you can also use it to measure angle, right? If you use it as a sensor, like your knob rotation, you can detect using resistance, right? By taking the value of the resistance, then you can measure the angle, the physical angle of rotation. Now, an LVDT is also detecting this displacement, but not angular, it's linear, okay? So this actuator actually comes down, and the extension of that distance is actually being measured, okay? So by touching it that way, now you know the height of it, because you know where this is located with respect to the table. So you have that distance measurement. And that's how you measure the thickness.
To detect the part height and flatness in 3 separate locations. The custom designed user interface details in real time the inspection data, tracking and storing the information. Custom software was used to incorporate all requisite measurement tools in the vision inspection. After inspection, the table indexes the part to the second 2-axis robot, where it is gripped and removed from the table and placed on an outbound conveyor for packaging. This Compass automation system made it possible for the end user to meet the standard.
Okay, so that's an automated inspection, like combination of the indexing table, pick and place, right? Everything there, but the purpose is not assembly, the purpose is inspection. So here's some more examples.
This automated dimensional inspection and material handling system was designed to inspect and serialize worm gear hubs for a customer located in Croydon, Pennsylvania. Parts are manually loaded into 6 in-feed magazines, each holding a maximum of 40 parts. When a magazine is actuated into the load position, a proximity switch is activated, alerting a 2-axis robot to the presence of parts. The robot, seen here, consists of a horizontal and vertical axis, allowing it to pick from all 6 in-feed magazines from various positions in each stack. The robot places a part into a 6-position dial table. At the first position on the dial, a sensor verifies that the part has been loaded correctly, and an air knife blows debris out of the inner diameter of the part, cleaning the part prior to inspection. At the second position on the dial, an air gauge mounted on a single-axis robot engages the part, measuring the inner diameter at 3 positions, top, middle, and bottom.
Okay, so it's actually trying to measure the inner diameter. So it comes in, and then it measures to the side, the inner diameter. Because this metal, I'm not sure what that is, a cutter maybe? The hole is probably punched. So when you punch something, there is usually the inner surface is not smooth. Sometimes you might have a smaller diameter at the bottom. So if I cut a section of this, so this is the hole, right? But if the punch starts to wear out, sometimes you can have that. I'm exaggerating, of course. So the bottom diameter is not the same as the top diameter of the hole. And that can happen. So that's why It comes in and it measures the hole diameter at 3 different heights. So something like that might be due to tool wear. So again, you don't know when your tool already worn out. You only know it after the defect comes out. So that's too late, way too late.
At the third position on the dial, a laser marker marks the part. Here, a shield surrounds the laser, protecting the operator from harmful radiation. Each part is marked with a 2D data matrix, consisting of the date of inspection, the shift number, and a discrete serial number. The air gauge readings for each part are stored to a database, enabling quality personnel to verify that each individual part has been passed inspection. In the final station,
that one's a laser marker. You remember in the trade show we saw a lot of laser marking device, right?
a smart camera grades the data matrix, ensuring that the code is legible. After
The data matrix is just a two-dimensional barcode type, just like QR. It's just a different type.
inspection, marking, and grading, the part is indexed to the offload position, where a pneumatic actuator picks the part and places it onto an offload conveyor. The machine processes one part every 10 seconds. This compass automation system made it.
All right.
Wasting too much time and resources hand-pulling cans throughout your canning run? With the BR30, you'll have automated inspection and inline quality control. The integrity of your product is important not only to you, but the consumer. With the BR30, you'll have peace of mind knowing that you're sending out quality packaged beer. Every can will be weighed for accuracy and visually inspected by our highly accurate vision system. Low fills, dents, and bad seams will be a thing of the past. The BR30, based on your parameters, will reject cans that aren't fit for consumer purchase. Ready for complete IP67 washdown, our system will drop right into your current canning line. TSC has hands-on industry experience, ranging from running multiple canning lines to testing seams and final package dissolve out. Be weighed for accurate inspection and inline quality control. Every can will be weighed for accuracy.
Okay, so they weigh the can. They also measure the diameter and detect any irregular seams on it. So it does a few things there. Sorry, I'm not sure of what they measure. Probably the dimension. Okay, here's a 3D scanner. Engine blocks. Obviously, not all dimension is the same importance, right? The cylinders, the height, and the flatness is more important than the outer body of the engine. Locations of holes is important, right? features. So he's doing a rework basically, right? If there are out of spec items, then he's gonna rework it right there and then. Lastly,
Scanners, each in different orientations. This system is designed to minimize user input. So pretty much what I mean by that is, it's designed so that you place a part on this rotary table, you press scan. Once that's done, the user does not have to touch or manipulate the data after the fact. So the data can then be used for reverse engineering or inspection.
this one is not exactly industrial automation purposes, but okay. Now let's look at a different kind of quality check, because we saw dimensional checks, right? Physical presence of holes, whether the holes are there, whether the resistor is there. So it's mainly visual. Now, what about assembly of bolts? How do you make sure that the bolt is properly tightened? And so, let's look at some examples of that.
These are the Tensor ST series tools from Atlas Copco. These high-speed, high-torque transducerized tools are made for safety applications where high productivity and full traceable results are required.
Okay, so this is what is called a DC torque tool. It's basically an electric wrench instead of pneumatic, like you see in a lot of car shops, right? If you ever hear the sound, whoop, 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 right? Those guns taking off the your wheels, those are pneumatics because you hear the wind, right? But in the factory, especially ones where you need accuracy, you're not going to do pneumatic, because pneumatic systems, you cannot really predict how much torque you tighten on that bolt. So if you want to have good control of that, you're going to need electric tools. And these have sensors in it to detect how much you actually tighten. And these are expensive stuff, like $2,000 each for tightening a bolt. I know. Can you do a torque wrench? Yes, but you want to do it fast. Hence, electric.
Ergonomic grips, long triggers, and a lightweight design help to reduce operator strain, while 4-color LEDs and an audible buzzer give clear feedback to the operator, helping to correct errors at the source. ST tools output 100% digital signals for torque and angle, allowing up to a 50-meter ST cable to be used to connect them to a power-focused 4000 controller. Having full rundown control from the controller provides
So here you can also program how you're going to tighten the bolt. So let's say you want first angle control, and then go to torque control, right? So I want to tighten it, certain rotations, and then you go into torque sensor. So you can do all this with certain speed and whatever.
excellent error proofing for assembly jobs. Accessories such as a barcode reader and program selector can be attached via built-in connection points on the tools. ETV ST right angle models feature a torque range from 1 to 4,000 newton meters at speeds up to 2,390 RPM. The ultra-compact one-piece angle head can fit into narrow, awkward spaces, and square drives are available in 3/8 inch up to 3/4 inch. ETD ST inline models feature a torque range from 1 to 4,000 newton meters at speeds up to 2,825 RPM. Certain models feature a telescopic spindle for fixtured applications with various line and mounting options. Square drive.
So these tools can also be mounted on robot arms too.
Drive sizes are available from 1/4 inch to 1.5 inches, and female hex drives at 1/4 inch. ETP ST pistol grip models feature a torque range from 1 to 20 newton meters and speeds up to 2,820 RPM. An easy access reverse button allows for quick direction changes, and lightweight design makes this tool great for low torque precision assembly jobs. Female.
The pistol ones are usually low torque. With high torque, it's usually bar, like that, right?
There's an air
A what?
That's part like air or?
No, it's electric.
But it looks like an air impact.
It's not. Oh, it's electric. It's fully electric.
It's pretty small.
It is. But the cables that is dangling is not a air hose. It's cables, right? So it's electric motor inside.
X drives are available in 1/4 inch and 3/8 inch. The SD tools require a controller to function, such as the PowerFocus 4000. The PowerFocus 4000 is an advanced process controller with full monitoring functions and internet infrastructure for networking capabilities. 2 varieties are available. The compact unit, which requires a PC connection and tools taught PF software to set up, and the graph unit, which can function as a standalone unit, act as a programming terminal for other PowerFocus units, and has a full color screen. The PowerFocus 4000 requires an RBU, or rapid backup unit, to function. Bronze, silver, and gold RBU units are available to expand the functions of the unit and back up important programming and network configuration. With a gold RBU installed, users have access to up to 250 PCEPs and storage for up to 8 traces, 99 jobs, and 5,000 status and data points.
So they actually keep track. You can keep track of how much a bolt is tightened for every one of your product. I got involved in one of the projects with these kind of tools for ergonomic purposes in Honda, and one of the amazing thing I find out is that they record how much torque they tighten each bolt that is safety related. So for example, the wheel bolts, the steering rack, anything suspension related, anything brake related. So if they scan your Honda, they know for your car, they tighten that bolt on November 5th, 2025 with 17.4 Newton meter. Okay, so they record every single one of these torque. Make a guess. Why would you do that? Huh? For what? Liabilities, right? So you drive your car, suddenly something get loose and you got into an accident, and you say, did you do it right? And Honda needs data to prove we did it, right? We did it on November 5th, 2025, your car at 2:54 p.m., this much torque, right? It's just legal protection, especially safety related, like airbags, brakes, wheels. Okay, so that's the power of electric tools. You can record all this. With pneumatic tools, yes, you can get a certain accuracy. Sometimes it's not the accuracy, it's the data recording that you want.
Advanced strategies such as yield control, step sync, home position, and snug rating are unlocked using the gold RBU. Plenty of inputs and outputs are available using open.
So it can also communicate to a central server, so everything is integrated.
Protocol serial, open, extra-rich tightening system. Best fits your Unique 4000 controller from Atlas Copco? If so, let us know.
Yeah, fancy stuff. Expensive stuff.
Ever since we started manufacturing fastening tools at Atlas Copco, we have done so under the motto, there is always a better way. Constantly pushing us to improve our tools and setting the standard in several industries. Our controllers have equipped our tools with traceability, result logging, and quality assurance. And now we're taking it one step further. We proudly introduce our newest control strategy, True Angle. When controlling a tightening, we either measure torque and control on angle, or measure angle and control on torque. This establishes a window that a successful tightening must land within. With True Angle, we set ourselves up to have more tightenings land within the window. It's a complex task handled by the PowerFocus 6.